So we have the presentations. We can have questions. I think we can leave the word free, and people can ask questions and bring up topics. So we have, of course, the topics we have talked about in the papers, in the presentations, and then we have the buzzwords here that I put on these slides to we could latch onto, for example. And we don't have a lot of time, but let's see where we end up. And you can raise your hand if you want to talk with pressing the raise hand button here in the WebEx. So anyone wants to start? Okay, I see there, and this obviously puts the raised hands on top, which is good. So then we have Christian Sauer, please.
Yeah, hi. I have one question for Tanguy, actually. This is on the unscheduling of SystemC threads. So why is this necessary in your case? Is it because you have potentially more threads than you have workers? Is this the answer?
Is it because we have more? No, the unscheduling we perform is only because one thread accesses a variable that is likely to create a dependency. Yes. We want to avoid them as much as possible, so we want to make sure the dependencies are handled in the sequential phase.
So, but why don't you just pause the thread until the dependency, like the shared variable, is not shared anymore? So it's unlocked, essentially. Why can't you just do that? Why do you need to unschedule this thread?
Well, I think this is equivalent. I mean, the point where you would be sure that the variable is not locked anymore is only once you have fully finished to execute the other thread that could have accessed it. So this would mean we would have to yield anyway to the point where we run into a sequential phase.
Okay, so your monitor is strictly passive. Is this what you're saying? The memory access monitor, it cannot block an access. Yes, right?
Yes, it does block an access. I mean, if you try and perform an access to a variable that is already owned by another thread in mod, for instance, then which is already owned, then your execution is postponed to the sequential phase, which is the same evaluation phase in the end, but it's still executed afterwards, after the parallel evaluation of thread that can run independently ended.
Okay, thank you.
Okay, thanks. Thanks, Christian and Tanguy. Let's move to Jakob.
I was probably last here, so maybe I should.
Okay, I was thinking that
this one just shows whoever put up their hands. Right? So
perhaps Mathieu, you were there first. Do you want to speak?
Yes, I have a question that's maybe a very broad discussion more than just a question, but about the dynamic versus static. I had some experience on static dependency detection in the past. And the thing is, obviously, you can do that only if you have the source code. And usually it only works if your control flow is simple enough. That is, typically, if you have a platform with dynamic binary translation, for example, QEMU or whatever, the control flow is going to jump from your platform to generated code with pointer to whatever and so on. And at some point, the static analysis is doomed in this case. Typically, the platform we study with Tanguy, we have the TLM platform, then QEMU, then Linux, then a compiled application on top of that. And I absolutely do not hope that we can do static analysis on this. Is there a way to fall back on dynamic monitoring in case the static analysis fails? I mean, it's really nice to have this static analysis because it can prevent stuff by looking at the future, which we can't in the approach we follow with Tanguy. But still, somehow we need a fallback to a dynamic approach when it doesn't work. I'm not sure that was a question or a remark or whatever.
Well, come to your mind, Rainer, this question before?
Yeah, I understand this is probably directed against me because I'm the one who did the static approach. Yes, I fully agree with what you're saying. That's the big disadvantage of static thing. The advantage is that you can actually look in the future, just like you say. The disadvantage is that oftentimes you need to be overly conservative. And whenever you're jumping into a region of code that you cannot analyze or there's only binaries, you need to assume worst case, meaning conflict with everybody, and then you are sequential again. 100% true. I think the real solution would be here in a combination of static and dynamic approaches. We could use the static on top of things, and then for things where there is the worst case situation, then switch to a dynamic approach. Maybe that would be one thing. And that could be future research, would be very interesting to actually look into.
In this way, it will lower the cost of instrumentation of the dynamic part to really relevant sections. I think that could make sense to have this kind of hybrid approach.
Yes, 100%.
So just to clarify, in the risk framework, when you do analyze for dependency, do you analyze also the guest software? And if so, to which extent?
Do we also analyze the guest software? Did I get that right?
Yeah, the guest software, the software executing on top of the virtual platform.
No, we do not, because the guest is basically then a binary that gets loaded at runtime from the outside. We do not analyze it, and you will only see the analysis of the, say, ISS in this case, where then there is a mem access to somewhere, and that becomes worst case, so it's a conflict. Yes.
Okay.
That's the problem that we have here.
Yeah. I mean, you basically have to write your ISS to be parallelizable, right? I mean, that is, but that's easy, right? Because you only need to write ISS comparatively rarely. I mean, you don't have that many CPUs out there. At least it's my experience. As I said, I mean, you have a few hundred CPU variants.
Yes, but the ISS will have access to memory, which you cannot predict, right? So statically,
exactly.
you're losing it. You need to do
yes, I mean, we do this all the time, right? It is technically complicated, but conceptually easy, right? You just need to have a protocol for the ISS to talk to your memory simulation in a way that preserves atomic semantics for the atomic instructions of the target instruction set. Everything else, you can just throw the data in. I mean, who cares about the order of accesses? It doesn't matter as long as you don't kind of make non-atomic stuff. Well, as long as atomic stuff stays atomic, you're mostly fine. And you can often cheat by kind of handing that off to the host platform. And then you need to do things like, keep track who's writing which pages, because if you have self-modifying code or a JIT compiler and fun stuff like that, of course, you have to invalidate your, ISS caches if somebody writes to the code which you have translated to something. I mean, there's a lot of these details, but most of them you have, even if you're running a serial ISS as well, because you have the same situation there with pseudo-parallelism. Real concurrency doesn't add all that much complexity, because you're already simulating, an arbitrary multi-core system. Right?
Yeah, I was also thinking if you simulate this multi-core system and if you have concurrency prevention that prevents these cores from accessing the memory, but they will access the memory in the real world, right? So you want to simulate that they can mess up the memory, but not in a way that's not happening in reality. So it's not all concurrency that you want to prevent, right?
No. Exactly. If two of them are clobbering, if the software is doing not properly locked accesses to data and memory, you want them to clobber each other. Or
yes,
be able to.
Simulator to detect that the programmer did a concurrency bug, right?
Yeah. Or it might just be okay, right? It might not even be a bug. It might just be behavior.
Yeah.
Yeah. So I have one question/comment in general. I mean, when we talk about this, one thing that strikes me is the fact that I believe we're thinking about different levels of concurrency, right? I mean, as I made clear in our talk, we have decided that it's enough to parallelize essentially across CPU simulators, the instruction set simulators, and then kind of attach a little bit of hardware modeling to each one of those. And that usually gives you enough parallelism. It gives you 10, 20, 30 units, which is sufficient, right? I mean, if you can make a simulator run 2 times faster, I mean, people are ecstatic. If we can get it, 5 times faster, I mean, that's an enormous result. If you can bring down the time to boot a platform from 100 minutes to 50, I mean, that's a huge victory. I mean, I've heard somebody say like 2x is small. No, 2x is major, right? If somebody's waiting for that result, making it twice as fast is fantastic. But I mean, what is the level of parallelism we should be thinking about? Because sometimes it feels like people think like, here is a little hardware unit, like a small computational block, or it's like in our case, it's most like here is here's a subsystem, right? Here's an instruction set simulator, or here's an instruction set simulator plus a few hundred devices making up, I mean, audio processing, image processor, Type-C subsystem, I mean, things like that, which contain, enormous amounts of firmware. And that's kind of a good enough level for us. I'm really wondering, how to think about the level of granularity. I believe you had it on your slide, Ola, right? Because I think that has a huge impact on what you're trying to do.
I recognize that point, Jakob. The thing is that the standard and also user guides and books are thinking into a sort of granularity at the SC module process level. And yes, you can say we should do the distribution at the kernel level, like you do. But there is no guidance for that. There is no API for that. There is no standard for that. So if we think that we should do SystemC in a distributed standard, that might be an interesting standardization effort on its own. On how should we standardize the API between different SystemC kernels?
Well, I mean, you can also say that
but we don't have that at the moment, so people are trying to do the parallelization at a lower granularity.
Yeah, no, it's more like an observation, right? Because I think to me, it might make sense to have a separate concept for this is a parallelizable unit, right? So you could say, like we have, the fact that I mean, our experience is it makes sense to take the giant simulation and kind of cut it up into smaller pieces, essentially. And that is kind of an intermediate level of, I don't know what we'll call it, granularity, splitting, subsystemness, whatever, right? Which you don't have in SystemC today. But I think that would be very handy. But then I'm in the same space as Rainer and trying to change the standard, right? But it feels like that is something that's almost always comes up when we do these things.
Or we should have something which is, like you say, subsystem level, that we need to standardize that, and that within such a subsystem, everything is sequential, but at the subsystem level, we need to think in more concurrent and parallel processes. But that's not part of the current standard, obviously.
Nope. But maybe that's the kind of concept that could be needed, because I see a lot of this kind of pointing in that general direction in a sense. And that could also simplify things like applying a compiler, because then you would say, yeah, I have this subsystem, I'm in control of it. I can use my source code compiler on that one, but I also have these imported 15 blocks from people who I don't trust at all. And I can just, lock them down and throw them into the serial boxes and run them in parallel to my nice subsystem, right? Because I believe in practice, you're almost always going to have binary models from people or badly written models. I mean, that's just life.
Yes.
I agree with this idea of doing the parallelism, also considering the parallelism at a more global level. But we still have to be cautious about. Okay, Jakob, you just decided that you would throw determinism under the bus, and that you don't care, and you don't care about debugging things. That's one opinion, but that's not the opinion necessarily of every users or every developers.
If you want debug, you tell it to run serially, right? Because we can switch at runtime.
well, if it's like, you know, it's the same situation as I've got a bug in my simulation, then I turn a switch. It can be, okay, put it in debug mode, and then that bug vanishes. That happens all the times in sequential programs. And so then obviously you are able to debug the non-bug. So this is something we have to, you know, pretending there is no problem with determinism
No, we don't.
is something that is quite bold as a statement. It may indeed be your case in your industrial case studies, but for sure this will not handle the problem at a more global level. So I was surprised, by the way, when hearing your presentation. You've got all the elements for being able to do some reproducible simulations, because you've got indeed that level of granularity for the parallelism means you control the communication between your various cells. For instance, you've got a network or you've got something that is well identified. It's not a shared memory anymore. And that's surprising to see that you just sit on the problem of determinism.
No, I mean, the network simulation is actually deterministic in SystemX. That part is deterministic. We can take, you can take an arbitrary simulation with an arbitrary number of machines. If you're using links between them with, you know, lots of details here, we've got papers on this, but essentially if you apply a certain minimum latency to the network, you have a simulation semantic which is completely independent of your actual execution. You can run it on one thread, you can run it on 100 threads, exact same semantics. The problem comes when we have sharing of tightly coupled things, basically memory and shared devices. That's when we realize that the amount of locking we would have to apply would negate the effect to a very large extent. Because typically we have extremely unbalanced workloads. I mean, we have an instruction set simulator. Some of it is running, you know, operating systems. It might be that the load kind of jumps around in the system. So what we do, and this is getting into the weeds a bit, but we apply temporal decoupling in parallel. So we tell every CPU that it can be at most X time apart from any other CPU. So they kind of move forward in rough time sync. Usually you would let them run 100,000 cycles for the fastest ones. So say that end up being 100 microseconds up to a millisecond. Might be milliseconds, but kind of high, but in the order of 10 to 100 to 1,000 microseconds is a possible kind of time deviation between two different processors, like the ones that is furthest behind and the one that's most ahead. And if you're the furthest ahead, you just have to wait until the other guys catch up.
Okay, that clarifies. Okay, I was a bit surprised. Okay, so basically we are seeing the same thing.
Yeah, but I mean, it also depends on what, you know, it kind of depends what you want your determinism for, right? It's one thing, now I'm talking too much, but I mean, the basic two different types of determinism here, I would say. One is, can my parallel simulation produce an execution that would also be found in a serial execution? That is one possible semantic. The other one is, can I, in theory, replay the same parallel execution again? That is repeatability and determinism, but the semantics might be different from the case where I run the same thing serially. At least to me, these are two different cases. It might be that if you say you want to be deterministic in the parallel sense, you could get a bit more freedom.
But it depends how you define the set of possible sequential executions. I think you can say anything without a precise framework. That was, by the way, a good thing we saw, for instance, in Tanguy's presentation. He had a clear example, and in that example, the result where you get, I guess, the value 1, if I'm correct, is definitely not the result you want to get.
Well, it's not a schedule that you can expect from any SystemC standard.
And basically, if you follow that line, you could say that that's the kind of reasoning we heard in the past. You could say, okay, let's throw out SystemC, let's do pthreads, and you will get whatever order, and we give perfect freedom to whatever threads, simulation threads we are running. And that way we have solved the problem of parallelization. So you see there is an extreme, which is you allow whatever order, whatever result, whatever unexpected result you would get if for some reason you forgot the memory protection, or you don't say there is any memory protection, by the way. That's the kind of thing, the kind of extreme things maybe not anyone would want. By the way,
I see a raised hand here from Carsten. I think it has been raised for a while. Perhaps.
Yeah, sorry.
Go
on, Carsten.
I have a question to Mathieu. So if you use an unmodified SystemC kernel, then I think you cannot use any more SystemC features inside your parallelized processes. Like if you use a data type like an scint, these data types are all centrally memory managed and using a lot of static variables so that your data will be meshed up and you will get crashes if you do this. Do you check this or?
Sorry, I didn't get who the question was addressed to.
Yeah,
To me?
there's an issue if you put some behavior in a separate thread, then I think you cannot use any or nearly nothing from SystemC anymore. If you use maybe an scint data type and local variable in your parallelized process, and you do it the same in another process with completely independent object, then your data will be meshed, or you get a crash.
Data type. Well, if your data type is something which doesn't have a static field, then it's okay. I mean,
but this is not the case for SystemC data types.
If there's a static field in the class for global memory management, then yes, you will get some issues.
Yeah, but the current SystemC kernel uses a lot of memory management and a lot of static variables for increasing the performance. So that's then my second, maybe a little bit provocant question. If we remove all this memory management and static variables, maybe our performance becomes worse. That it's neglects a little bit the parallelization. So I don't know it, but at least what I saw currently with the current SystemC implementation, it's, for my opinion, nearly parallelization or also parallel action, parallel connections of tools. It's nearly not possible because there is so much central data structures inside the code, so that if you do not remove it, then it's, in my opinion, it will not work.
Yeah, so in my case, I really focused on parallelizing code which doesn't call SystemC, and typically this is what happens when you have an algorithm which is memory CPU intensive, and that you wrap it in the TLM platform. Typically, you have a video encoder, decoder, or whatever, and you build a model of a hardware accelerator for it.
Okay.
Then the piece of code when you spend a lot of CPU time is not related to SystemC.
Okay, yeah, then
it's really efficient to just delegate it to another thread, and I still have that SystemSC call method to allow falling back on the SystemC world, and then you have thread safety for a specific portion of code. Obviously, if you need to call SC call all the time, you will get a lot of costly synchronization, and then you lose the performance benefit.
Yeah, but what I think currently you cannot use nearly no SystemC feature inside your behavior code. And I would think.
I can use it using that SC call feature, which just takes a piece of code, typically a lambda, and sends it to SystemC. Actually, what I didn't mention in the talk is I have also async SC call, which sends a piece of code without waiting. So you know the piece of code will be executed as soon as possible in SystemC, but you don't have to wait for the end of a SystemC process to continue your execution on the SystemC side. So if you can do that thing asynchronously, and if you don't need to wait for the result, then the performance cost is a bit lower.
Okay, yeah. Okay, thanks.
I just make a short comment. We actually have the exact same mechanism in SystemC, where if you have your own thread and you want to call the SystemC API, you have to use a special callback mechanism that gets you into a state where you're actually safely synchronized with the SystemC core scheduler itself. So I think that's a pretty good mechanism, actually. I mean, it means if you have tons of code which basically is kernel independent, that's a decent way to deal with that problem, because if interactions are rare enough, it works. If people use it too often, it just crash performance.
Do you forbid in SystemC to use SystemC data types then inside threads?
No, because as we said, we decided we have to be ABI compatible. So each and every SystemC subsystem has all these limitations. Standard SystemC is not based on SystemC, so there we can do anything we want. So we're just using C types, and we have thread safe memory allocators and all the services you would expect, because we have our own kernel, which is not constrained by any kind of standard. We are perfectly fine to rewrite it every few years, throw things out, change stuff according to our own rules, which is definitely an advantage if you want to move quickly, but it also means
That means you encapsulate in each thread an own SystemC instance, and you ensure that only your behavior code only accesses to this one instance. That means if you have different threads, you will have different SystemC instances.
Yes, if you have multiple SystemC subsystems and you run them in SystemC, they will run potentially on their own threads, and they will be considered isolated. And when they reach outside of their SystemC environment, they will use the SystemC APIs with all the attendant locking and safety across the threads. So essentially, just like everything else in SystemC, we take the basically serialized code and give it a serial environment in which it can run, and then we just put many of these serial environments in parallel to each other, which works perfectly for the use case we are seeing today when a system isn't. I mean, we're not modeling a super parallel compute system. We're usually modeling this extremely heterogeneous collection of independent subsystems.
Okay.
And that means, Jakob, when you run these multiple SystemCs, it's the same thing as if multiple SystemCs were running as separate programs in Linux. The same effect.
Yes, except for the fact that they are speaking inside the same process. You don't have to worry about things like inter-process communication, sockets and stuff, right? We're still just using function calls.
Yeah.
To get out. It's kind of an in-between. But yes, for the SystemC code, it looks like I am my own program and I'm running in my own world, and stuff happens at the boundary.
I see that time is running. It's 2 minutes left. Any final words, anyone?
So maybe I have a question, Ola, and let's see if this helps to conclude on this. From my limited observation, we seem to be looking at two different worlds for parallelization. There are those that actually sit on top of SystemC, and they are trying to modify the code or partition the model, or maybe even branch on multiple SystemC simulators, right? So we have seen a couple of instances today. Then there may be also more works that actually try to accomplish parallelization, let's say from within, without changing the model too much, right? Recompiling it in a different way, analyzing it, or maybe have a different kernel, right? So when it comes to impact on the SystemC standard, right? So my question probably would be, what's the least thing we have to do in the standard to support maybe the world of explicit parallelization on top of SystemC better, right? Or what is the least thing we need to do on the standard, on the implementation, right, on the library, to actually maybe enable also more concurrent approaches better? Yeah. So I'm not sure what this audience has to comment on this, right? But if we had like a concurrent, a thread-safe SystemC kernel, would this make our life easier? One question, for instance, to ask. Or another one might be, was this question asked and answered before, like all this SC pending activity, right? for instance, these APIs, are they actually being used by anyone actively? I think, Rainer, you asked this question before as well. So it would be interesting to see these things.
Thank you for pointing this out. I agree with you very much. I see a big obstacle in changing anything in the standard at this point. I think everybody has settled on the agreement that the standard is not great, but we need to work around it. I'm personally still interested in to see whether there's any interest out there to change anything in the standard, or do we always stay at 2.3.x SystemC? Can we ever go to 3.0? Maybe that's too radical and probably beyond this group here. But anyhow, this group is 50 people or so. They are interested in this. Maybe we can make something moving.
In a world with competition and some market forces, I guess if we don't change the standard, we will be outmaneuvered by the competition. I mean, someday SystemC will be the thing that we did long time ago, but doesn't work. So I think we should view it also as some kind of competitive world where perhaps we need to shape up.
I would like that.
And by the way, if we want to really change something, it will not be a 3.0 or 2.4, because this is actually the version of a specific implementation, which is the one of Accellera. And we have also to deal with the commercial implementation. So it would be more like, C++ 11, 17, things like this. We are preparing IEEE 2000 and I don't know, 22, 23. Maybe it will be 2000 and something, hopefully.
Okay. But I think those were nice final words. Thanks, everyone. Especially thank you to the speakers and presenters. This has been really interesting. We have the recording and you have pitched in with links to your slides. I think if you have not, please do that after the meeting so we can collect this information. And we have the systemc.org where everything lives nowadays. And thanks to Martin for maintaining that. It's really cool. So yeah, let's meet again later on. And as a final word, I will just put up my teaser again for the next Fika in September. We are planning and then to move outside of the electronic systems computer simulation, so to speak, and to see if there is a way to simulate with respect to safety. So I conclude with that. Thanks everyone again, and have a nice rest of the day.